Should I minimize?
Yeah, I think if we used to have a bit.
I could just move those people over here. That's good. That makes sense. Good. I think it's the top right one. No, that's better. There we go. That works. Yeah. All right. So, welcome to last lecture of the school. So we're hopefully this will be, slightly easier than what we've been doing for the couple last days. I'm not entirely sure. Well, we'll find out. But it's been fun teaching you guys. It's an engaged crowd. So what we're going to be talking about today is the connection between exact and parameterized algorithms for the satisfiability problem. And then we'll do, if there's time, a acute approximation algorithm for tournament feedback vertex set. They're saying there's no video. There. Is the video working now? There's multiple people with rainbows behind them. Yeah. Okay. All right. So in the k-sat formula, you're given a k-sat problem. You're given a formula phi in k conjunctive normal form, or KCNF, which means that the formula consists of m clauses, each one on at most k literals. Every literal is a variable or its negation. And there are n variables, and the task is to figure out whether the formula phi has a satisfying assignment. So here is an example of a 3CNF formula phi, x or not y or z, and not x or not y or z, and x or not p, and not x or p. And an assignment, we want to set the variables to true or false. So for example, if we set all of the variables to true, then all of the clauses are satisfied. The blue arrows now point to the literal that satisfies each of the clauses. However, for example, if we set x and z to false and y and p to true, then the formula phi is not satisfied because the first clause would be false. Yeah. So if x and z are false and y is true, then there's nothing to satisfy this clause. Of course, this is the NP-complete problem, right? When you learn about NP-completeness, this is the first problem you see. And there is a naive 2 to the n algorithm. Just try all possible assignments and see if they satisfy the formula. It's worth mentioning, even though it doesn't really have much to do with randomized algorithms, that the exponential time hypothesis and the strong exponential time hypothesis to some extent says that brute force is the best you can do for SAT. So the exponential time hypothesis says that you cannot do SAT in sub-exponential time, so you cannot do SAT. So there exists some universal constant c such that 3SAT requires c to the power n time. Yeah. So 3SAT requires 1.000001 to the n time for some fixed number of zeros. And it's just a conjecture, which happens to be very useful for showing running time lower bounds for other problems. The strong ETH postulates something even stronger. It's not immediately obvious from the statements that the strong ETH actually implies ETH, but it does. The strong ETH postulates that for every epsilon, there exists a k such that there is no algorithm with 1.9999999 to the n for a fixed number of nines to k sat. Or for every fixed number of nines, there exists a k so that k sat requires 1.999 with that many nines. Yes. So now the question is, well, can we still do better than naive? Well, if we don't want to disprove ETH or strong ETH, then better our algorithms should all be, exponential time. They should all be c to the n for some constant c. And also this constant c should converge to 2 as k tends to infinity. However, we can hope for getting below 2 for each fixed value of k, right? We can hope to get below 2 to the n for 3 sat, for 4 sat, for 1000 sat, and so on. Okay, so let's try at least to get below 2 to the n for 3 sat, right? And in order to do that, we're going to turn to a problem that you already saw in the tutorial and look at a parameterized algorithm. So I'll define, d-bol k-sat or d-local search k-sat to be the following problem. I give you as input a KCNF formula phi and an assignment to that formula and an integer, and I ask, does there exist a satisfying assignment to the formula that is at most distance d from the one I gave you? Yeah, distance d means you're allowed to flip at most d variables. Yeah. Now, of course, if the assignment I already gave you is satisfying, then the answer is yes. You can just output it. Otherwise, you now need to search, in the d-bol around the assignment that you have been given, and you're asked to get an algorithm with running time k to the power d. Let me give you the algorithm in case you didn't have time to look at that problem. So if alpha already satisfies phi, you can return alpha. Otherwise, pick your favorite unsatisfied clause C, pick a literal from that clause uniformly at random, and flip it. And now with probability 1 over d, you're moving one step closer towards the unknown optimum solution alpha. In particular, you know that for at least one of the literals in the clause C, alpha must satisfy the clause, so alpha must currently differ from beta, so beta is the unknown assignment. So beta must satisfy the clause, and alpha doesn't. So they currently differ in at least one of the positions. So when you pick a position uniformly at random, then with probability at least 1 over k, they go from differing to not differing at that position. And if you succeed k times in a row, then your current solution is equal to the satisfying assignment, and you would have found the satisfying assignment. Now you can repeat this k to the d times to get success probability 1/2, meaning that you get a k to the d time algorithm. All right, so here's a question. I claim that this already gives me an algorithm with running time better than 2 to the n for 3 sat, something like 1.75 to the n or something like this. So can someone suggest how I can use this bol-sat algorithm to get below 2 to the n for 3 sat?
Half of the assignment we made true, then you start searching.
Pardon? So we could you could try searching from the all true assignment. Yeah. So notice that the distance from the all true assignment,
Half of the assignment is true.
half of it true and half of it false. Yeah. So yes.
All 0 and all.
Yeah. So what happens if you do bol-sat search from all 0 and from all 1? You know that every assignment is a distance at most n/2, either from all 0 or from all 1. So if I do d-ball search for d equals n/2, once from the all true assignment and once from the all false assignment, if there was a satisfying assignment, I'm going to find it. And what is my running time going to be? Well, it's going to be 3 to the power n/2, right? Because if I'm doing 3 sat, k is equal to 3, d is equal to n/2. Yeah, so k to the d is 3 to the n/2, and 3 to the n/2, that's square root of 3 to the n. So that's like 1.7333 to the n. Now, what does this give me for 4 sat? Well, not much, right? It's 4 to the n/2, which is still 2 to the n. So for 4 sat, or for k sat greater or equal to 4, I'm actually doing worse than brute force. But I got something for 3 sat, right? So like, okay, that's good. So the reason somehow we're failing for 4 sat is we are spending too much time in our ball search. So somehow but we're trying to start our search in 2 positions, right? So what if we tried starting in more positions, but having a smaller ball that we're searching? Maybe we could win then, right? And that is roughly what we're going to try to do. Now the question is that, well, when you only have 2 positions to start from, it's sort of easy to figure out that the all true and the all false is the right thing to do. However, if I tell you, well, I have 10 starting positions, or like 100 starting positions, or exponentially many starting positions, it's not obvious where to put the starting positions. So in particular, this ends up being the question of finding a good covering code. So this you end up going into coding theory. However, from an algorithm's perspective, we don't even need to construct these codes. Nice thing is, if you just pick starting points at random, you're going to do great. So that's what we're going to be doing now. So here is so suppose we have a C to the D algorithm for d-ball sat. Yeah. Then I'll give you an algorithm for sat. All right. I'll pick d, so my integer, cleverly based on the number of variables in the input, and c, so the base of the C to the D algorithm for d-ball search that I have. And then I'm going to repeat, some number of times. We'll figure out what number of times that is. The following procedure: select a random assignment and solve d-ball sat from that random assignment input time C to the D. If I find a satisfying assignment, return that I found it. And if I haven't found one after a bunch of repetitions, then I say that the formula is unsatisfiable. Okay. Exactly, yes. Yeah. So you want to just determine whether such a thing exists or not. Yeah. So now the question is, how many times do we need to repeat it? Well, when I pick a random assignment alpha, suppose, like, when do I succeed? Suppose there exists some satisfying assignment beta somewhere. Yeah. If alpha is in a d-ball around beta, then I succeed. Right? So the number of places, like the number of choices for alpha where I would succeed is the size of a d-ball around beta. And what is the size of a d-ball? Well, I claim that it's n choose d. I just tell you which positions to flip. And if starting with beta, if I tell you which d positions to flip, that will determine all locations in the d-ball around beta. Yes. D-ball, because we're working with Hamming distance, right? So I mean, it's a distance metric. If I'm saying, well, everyone at distance 1 meter away from me, right? That's going to be a sphere around me. Yeah. And now we are in n-dimensional space, and of course, it's not continuous, but it's nice to imagine it as some sphere around the point. Does that answer your question?
You need to sum here. Some DA is going to work to be.
Yes, technically you need to do that. However, you know, and so as long as d is less than n over 2, right? It's like n times that. So details. Okay. So, and there's 2 to the n assignments. So how many times do I need to repeat? I need to repeat 2 to the n over n choose d many times. Now, notice now I'm underestimating my success probability. So now this ends up being correct, right? Like, yeah. So I underestimated the size of the ball, which means that now I'm overestimating the number of times I need to repeat. So this is still going to be fine. So I'm going to repeat 2 to the n over n choose d times, right? And then I know that with high probability, at least one of my starting points will be within the d ball of the satisfying assignment, and then I'm going to find it. So what is my running time? Well, it's 2 to the n over n choose d times c to the d. I mean, like, this should look familiar from day 2. So what should we do with d? Well, we should pick d to minimize this expression. Okay, so now here's the thing. Last time, this was an expression that was actually really tricky to optimize. This one is surprisingly easy, so I'm actually going to do it rather than telling you, just trust me that this is what it turns out. I can actually figure out what it is. All right. So what is my running time? It's the minimum over all choices of d less than or equal to n of 2 to the n over n choose d times c to the d. Right? That's our expression. Now let's do something crazy and saying, well, if I want to minimize f of d, that's the same as taking 1 over the maximum of 1 over f of d. Yeah, so maybe, yeah, like in I guess you see this, right? Like if I'm, so if I take this value and I'm trying to minimize it, then that's the same as maximizing its inverse. And then if I find the maximum of the inverse and I take 1 over that, then I get the minimum back. Yeah. So, all right. Seems like a crazy and useless thing to do, but let's do it anyway. Now, at the bottom here, we have a maximum, right? And I claim that, so by the way, what are we trying to do with the running time? We're trying to upper bound the running time, right? Which means that I want to replace, say that something, that this is less than or equal to something, right? So if I make my denominator smaller, then I make the whole fraction bigger, okay? So we want to replace this by something that is smaller, but it's easier to analyze. So, well, okay, the max of a bunch of numbers is never bigger than the average, right? Like max d less than or equal to n of this is less than or equal to the sum d over n of this divided by n. Yeah, so this is at most here, right? So yeah, so max is bigger than the average. The average is smaller than the max. Yeah, so if I replace the max by the average, then the denominator got smaller and the whole fraction got bigger. Okay, all right, we did. Okay, now, we do some cleanup. The 1 over n plus 1 term, I can move it out. The 1 over 2 to the n term is independent of d, so I can move it out. And I get this kind of thing, right? N plus 1, 2 to the n. And on the bottom, I get the sum of d equals 0 to n choose d. I had c to the minus d. I rewrote it as 1 over c to the d. And then I multiplied it by 1 minus n minus d. And some of you might anticipate what's coming now, right? Now we can just apply the binomial theorem, because now it's n choose d times something to the d times something to the n minus d. What did I do wrong now? Shouldn't be touching things. Where is this? This one?
Yeah, in the-
That's not what I wanted. Okay, let's see. There, oh. Okay. Wait, why is this still so? I feel it's still. Whoa, which one is this? Ah, there we go. This is like backwards view. Full screen. Okay, that's better. All right, thank you. Okay, so okay, so what's coming? The binomial theorem, right? So this is nothing but 1 plus 1 over c to the power n. Yeah, so this ends up being n plus 1 into 2 to the n over 1 plus 1 over c to the n. And now, I just do some cleaning. Nothing interesting going on here. And I end up with n plus 1 into 2 minus 2 over c plus 1 to the power n. Yeah. Okay. So now we can think, like, what does this mean, right? We have a 3 to the d algorithm for 3 sat. Yes. So c is equal to 3, then c plus 1 is 4. 2 minus 2 over 4 is 1.5. So you get the 1.5 to the n algorithm for 3 sat. What about 4 sat? That's 2 minus 2 over 5. So 1.6 to the n algorithm. Yeah. What about 19 sat? That's 2 minus 2 over 20. Yeah. So that's 1.9 to the n. Okay. So you're actually getting something for every value of k. You're below. It's like 2 minus 2 over k plus 1 algorithm for k sat. Yeah, so these are the examples. Okay, of course, obvious question, can we do even better? Yeah. And in order to do that, it's enough, we should observe the following. When we were doing this ball sat, right, we were actually doing the following thing. I give you an alpha and I ask, does there exist a satisfying assignment at distance at most d from alpha? But it's enough for us to do the following, that if there is a satisfying assignment at distance at most d, output any satisfying assignment, even if it's far away. Yeah, so you don't really need to determine whether there is a satisfying assignment at distance at most d. It's enough for you to be like, if there is a satisfying assignment of distance at most d, then report that the formula is satisfiable and give a satisfying assignment. And that is what we're going to try to do, and we're going to do that, in time better than k to the power d. Yeah. So the algorithm for this permissive Bolsat version is pretty much exactly the same as before. Yes. So the difference, so in normal Bolsat, I give you an assignment and I ask, is there a satisfying assignment that is close to the one I started from? Then if the formula is satisfiable, but the satisfying assignment is far away from the one that I give, I should be reporting no. Yeah. Now for the permissive version, I give you a starting assignment and I say, if there is a satisfying assignment that's close, you should say yes. Now, if there isn't one that is close, but there is one or there isn't one that is far away, you can report anything. Yeah. So in particular, if there is a satisfying assignment that is far away, you can point to it. You're free to output that assignment. Yeah, but you don't have to. Yeah, that's why we call it permissive, because we're requiring less of the algorithm than in the other one. So what's the algorithm? The algorithm is basically the same as before. You just start with you start with the assignment you're searching from, and if it satisfies the formula, then you return the assignment that you have. Otherwise, you pick an unsatisfied clause. You pick literal at random from the clause, and you flip the literal in your assignment. And the only difference between this algorithm and the previous algorithm is the previous one just went for d steps. And this one we're running it for a bit longer. Let's say n square steps. This n square is subject to change. Okay, let's think of it as some polynomial to be determined later. Okay. So now let's try to analyze this this algorithm. And in order to analyze this algorithm, we're going to go to the analysis of random walks with the drift. So now I need to do a little bit of tutorial on random walks. So what we're going to do is we're going to track the distance from, so we're going to fix some unknown satisfying assignment, let's say beta, and we're just going to track the Hamming distance from gamma to beta. Yeah. Initially, it's d. It's at most d. In the worst case, it's d. Yeah. And in every step, we know that the probability that the distance decreases by 1 is at least 1 over k. Yeah. And with probability at most 1 minus 1 over k, it increases by 1. And that's the only two things that can happen. The distance actually cannot stay the same. It's either decreases by 1 or it increases by 1. It decreases by 1 with probability at least 1 over k. And if it doesn't decrease, then it increases. Yeah. Now we can compare this with a random walk with downward probability 1 over k. So what does this mean? Suppose a random walk with downward probability p, or like equals 1 over k, and a starting position d. And today we're only going to be considering k to be greater or equal to 3. Yeah, so we're interested only in walks where the downward probability is 1 over k for k greater or equal to 3. So what is this? This is just a sequence of random variables, p0, p1, p2, and so on, which encodes the position at time 0, 1, 2, 3, 4, and so on. And at every time step, you either move down or move up. You move down with probability 1 over k, up with probability 1 minus 1 over k. Exactly. So formally, what we can say is that p0 is equal to d, and pi is the sum of j from 1 to I of xj's, where the xj's is just a sequence of independent -1, 1 random variables, where xi is -1 with probability 1 over k, and 1 with probability 1 minus 1 over k. Yeah. So that's what a random walk with a downward probability 1 over k is, right? You just take a bunch of independent 0, -1, 1 random variables, and you add up a prefix of them. And that's what your position is at any given point of time. Okay, I'm going to say that the walk reaches 0. I mean, this is an infinite sequence. The walk reaches 0 if there exists some I such that pi equals 0. If at any point of time you are standing at 0, that means that the walk reaches 0. You reach 0 in at most s steps if there exists some I less than or equal to s, such that pi is equal to 0. Yeah. So are the definitions okay? Any questions? Yes, exactly, right? Because pi's are the positions. Pi plus 1 is equal to pi plus xi plus 1. Yeah, just by definition. And therefore, pi plus 1 is equal to pi minus 1 with probability 1 over k, and plus 1 with probability 1 minus 1 over k. Yeah, so this is what this thing looks like, really. Yes. So p0 is d, and pi is the summation of xi's up to. Pardon? Yeah, there is no. Yes. So the random walk, it can take negative values, right? So I'm now defining what a random walk is. Yes, I've so far not connected it at all with what is happening in the SAT algorithm. Yes, and so yes, it's good to note that this thing, so a random walk here can take negative values and can take arbitrarily large values, more than n. Yes, our algorithm will stop when we reach distance 0. A random walk just continues forever. Yeah. So so far, there is no connection between the algorithm and the walk. So far, we're just, here is a random walk, we're going to study its properties, right? Like, has nothing to do with the algorithm, but I will give you a claim that connects the two. Yeah? Yes? P, yeah, 1 over k, yes. So P here, P is equal to 1 over k. Pi is equal to sum over one of the xj's, where the xi's are in the sequence of independent random variables. Exactly. Yeah, so P naught is equal to D. So D is the starting position. Oh, yes, of course. Thank you. Come on. Okay, I guess I restarted, so my pen isn't paired. There we go. Come on. Thank you. No, okay, I'm not gonna fix it. It's fine. All right, there should be a P naught plus there. Okay. Yeah, you're right. Okay, so we've defined what it means for the walk to reach 0, and we've defined what it means for the walk to reach 0 in s steps. And here's the claim. The claim is that the algorithm, so for any integer s, the probability that the algorithm succeeds in at most s steps is at most the probability that a random walk from D with down probability 1 over k reaches 0 in at most s steps. Yeah. And this is an intuitively obvious statement. However, I mean, if you want to actually prove correctness, you need to prove it. And I'm going to sketch the proof. Well, for every step, the algorithm goes down with probability at least 1 over k. That's the sketch. And for proof, you have to do that in the tutorial. Okay. In particular, but I'll tell you exactly what to prove in the tutorial. You want to prove the following thing: that for any number of steps, so for any s, and any starting and any position j, the probability that the Hamming distance from alpha to beta is at most j in step s is at most the probability that the walk is in position at most j in step s. Yeah. So if you just prove that by induction, then the claim follows. Yeah. So you do that by induction on s. Okay. So in particular, because of the claim, we can now forget about the algorithm and just focus on what is the probability that a random walk that starts at D and has downward probability 1 over k reaches 0 in at most some number of steps. But for now, let's forget about some number of steps. Let's ask, what's the probability that it reaches 0? Because here is the thing. That probability isn't 1. Because the walk has an upwards drift. You go down with probability 1/3 and up with probability 2/3. So if you actually try to sample these things, what happens is that they tend to drift upward. Like, sometimes they go down to 0 and then stop. I mean, like, then you're happy because they have reached 0. I mean, they're going to go up again. So sometimes that happens, right? But most of the time it just drifts nicely off into infinity without ever touching zero. Yeah. So we will now be interested in the following question, rather than what's the probability that it reaches zero in S steps. We'll just ask, what's the probability that it reaches zero at all if you start from D? Okay, so I'm going to define Qi to be the probability that the random walk with down probability 1/k eventually visits zero. Yeah, if you start from I. Okay, Q0 is 1. You start at 0. Q1 is already non-trivial. What's the probability that you eventually reach 0 if you start from 1? And here is a fun analysis for Q1. You start at position 1, and then in the first step, you go down with probability 1/k and up with probability 1 minus 1/k. Yeah? And now we ask, well, what's the probability that you're going to eventually reach 0 from position 2? Well, that's Q2. Okay, we've written Q1 in terms of Q2, but that's not very nice. We want to write Q1 in terms of Q0, not in terms of Q2. But you know, if we want to reach 0 from 2, we need to eventually visit 1 first. Yes? And what is the probability that you visit 1 if you start from 2? Well, it's the same as the probability of reaching 0 if you start from 1, right? Because you just shift all of the integers down. So the probability of eventually reaching 1 if you start from 2 is Q1. And then the probability of eventually reaching 0 if you start at 1 is another factor of Q1. Yeah, which in particular now means that Q1 is equal to 1/k, the probability of going down, plus 1 minus 1/k, the probability of going up, times Q1 squared, right? First you need to go to 1, and then you go to 0. Okay, so now this gives us a quadratic equation. If you throw the quadratic formula at it and do some factoring, you'll figure out that Q1 is either 1 or 1/k minus 1, right? If you don't believe me, you can just plug in these two values and say that see that this actually turns out to be 0, and okay, a quadratic formula now has at most 2 roots, so these are the roots. Yes. Okay, so Q1 is either 1 or 1/k minus 1. It can't be both. It's actually, I mean, it's a probability, right? It's one or the other. So which one is it? Okay. Well, what would 1 mean? 1 means that every random walk, well, with probability 0, the walk goes off into infinity without ever touching 0. Yeah. So every walk that starts at 1 touches 0. Yeah. So the probability mass is actually 0. Right? Like there's not a single walk that starts at 1. Yeah, and that seems kind of fishy, doesn't it? Right? The probability isn't 0, right? I mean, there is a walk that starts at, there is a walk. Well, okay, no, it's actually non-trivial because so now you want to say you want to prove that not every walk. I think I negated the thing that I wanted to say. Right? You want to prove that not every walk that starts at 1 tends to infinity without ever visit 0. No, I'm messing up again. Okay. Q1 is the probability that you will visit 0. Yes. Q1 being 1 means that every walk visits 0. Yes. Yes. Okay. It's not quite that every walk visits 0. It's the walks that do not visit 0, yes, have 0. Is this the correct? Yes. Let's see.
So it's like you prove that Q0 is 1.
I okay. So Q1 is 1 means that with probability 1, you will visit 0 before you drift off upwards, right? Which one can prove isn't true. I'm going to ask you to prove that it. So I'm trying to think if I missed something and there's like an obvious way of stating that it isn't true, but I don't think there is. So I think the thing I'm going to ask you later is so in particular, proving that Q1 is not 1 is a non-trivial task. Okay, and I'm going to make you do it. But towards that, and something that will turn out to be useful anyway is, well, we don't quite know what Q1 is yet, right? It is 1 out of 2 options. But let me prove to you that Qi is equal to Q1 to the power I. Yeah. Well, okay. If I start at I and I want to reach 0, then the probability that I eventually visit I minus 1 is Q1. Yeah? And then the probability that I eventually visit 0 is Q1 times Qi minus 1. And then by induction, that is just Qi minus Q1 to the power I minus 1 times Q1, which is Q1 to the I. Okay. So in the tutorial, I'll ask you to prove that for every k, so for every downwards probability, 1 second, there exists a j, so that if I start my walk at j, then the probability that you eventually reach 0 is at most 1/2. So it's not 1. Right? There exists a position so that if you start the walk at that position, isn't 1. Yeah, and you can prove that either by directly looking at binomial distributions, because your x's are either 1s or minus 1s. So the number of x's up until a given position that are 1 are binomially distributed. Or you can use the Hofstadter bound, whichever one you prefer, to show this kind of statement. Okay? Assume that you're able to show this statement, then I claim that this proves that Q1 is not 1. Why is that? Exactly.
If there is a Qi which is less than
half,
then it's not.
Yeah. Right. If Q1 was 1, then Qi would be 1 for every I. But if we now show that there is a j so that Qj is at most 1/2, then Qi isn't 1. No, Q1 isn't 1. So therefore, Q1 is 1 over K1, and Qi is 1 over K minus 1 to the I. Yeah. What does that tell us about a randomized algorithm? It means that if we could run the local search forever, yeah, then the probability that it would find a satisfying assignment is at least 1 over K minus 1 to the D. D is the starting, like I here is the starting position. That's better than 1 over K to the D. Yeah, it's 1 over K minus 1 instead of 1 over K. For 3-sat, it would be 1/2 to the D instead of 1/3 to the D. Yeah, but we can't run our local search algorithm forever. We want to run it for, n square steps, or polynomial in n many steps. So now what we really want to do is we want to figure out what is the probability that you reach 0 in not too many steps, let's say order D steps. Yeah. And what we're going to in the tutorial, I'll have you prove that this probability is actually QD over 2. Yeah. So I'm going to skip that argument that, well, eventually it reaches 0 with probability QD, which is 1 over k minus 1 to the d. I'll have you prove that if I stop the local search after not too many steps, I actually only lose half of my success probability. And losing half is good. That's like QD, like 1/2 of an exponential of 1 over k minus 1 over 2. It just doubles the number of tries I need to do. Yes, it doesn't double the base of the exponential. So in particular, what this means is that a walk from d with down probability 1 over k reaches 0 in order d steps in 1 over k minus 1 to the d times 1/2. That gives a 1 over a k minus 1, or big O of k minus 1 to the d algorithm for permissive d-ball k-sat, which in turn gives us a 2 minus 2 over k to the n algorithm for k-sat. Because remember, the translation of the exponent for permissive d-ball sat to k-sat was a 2 minus 2 over some like c plus 1. So that's k minus 1 plus 1 is k. Yeah, that's where that came from. So what does this give us for 3-sat? It's also already a quite nice number. It gives us 4 over 3 to the n for 3-sat, right? 2 minus 2/3 to the n, that's 4/3, 1.3333 to the n. It gives us 1.5 to the n for 4-sat. The best known algorithm for 3-sat runs in time 1.30 to the n. So this is already very close to what is the best known. Okay, so here are the tutorial questions I'll ask you in order to show this green statement, but okay, we can wait for that until the tutorial. Where did we use that? Aha, we used it in one place. What does our local search algorithm do? It starts at the assignment we started from, and then it runs for like n square steps, and so and it goes. It now flips some literal, right? It flips some literal. And if the satisfying if the assignment it has is satisfying it, it returns that it is, right? But you run the local search for more than d steps, right? You run it for like order d steps. So it could be that at the time that you succeed, you've actually moved further than d away from your starting assignment. Yeah. So even though there was an assignment, right? Like, so what could happen was, maybe let me do it here so the Zoom crowd can see. So the question was, where did we use that it's permissive? So we start at alpha. So alpha is our start. And beta is some satisfying assignment that's in our ball, right? And now what could happen is that our local search travels outside of the ball and then finds a satisfying assignment. And when it finds a satisfying assignment, it doesn't, I mean, it cannot, we can't continue our local search at this point because we don't have a clause to branch on. Yeah. So in particular, even though the analysis is all with respect to beta, yes. And if we could have continued the walk when we found the satisfying assignment here, then we would actually be able to solve normal d-ball sat. Yeah. But the point is that when we reach the satisfying assignment, we don't have a clause to branch on. So we are not able to continue the walk. We have to stop at this point. And so that's where we use that as where permissive. Well, thanks for that question. Let me remove this. Okay, and now, so in the tutorial, I will, have you show this success probability thing, and now do something completely different. So before we go there. I know. Are there more questions about the satisfiability algorithm? No questions from Zoom? No. Okay. So we'll be looking at the following problem: tournament feedback vertex set. So a tournament is again a directed graph, so that there is an arc in one of the two directions between every pair of vertices, right? So every pair of people play some game, and then there's a winner and a loser, and you orient from the winner to the loser. And we looked at the feedback arc set problem earlier, where like what is the minimum number of results that you needed to change so that we could rank all the players from best to worst. Yeah. Now in the tournament feedback vertex set, we're asking what is the minimum number of players you need to disqualify so that you can rank the remaining ones from best to worst. Yeah. Or where you have the weighted version where every vertex has a weight, and you ask what is the minimum number, what is the minimum weight of a vertex set, so that after you remove them, you can rank everyone from best to worst in a consistent manner, right? So that T minus S is acyclic. So this is also an NP-complete problem. It has an easy factor 3 approximation algorithm, which I will have you do in the tutorial. But what we're going to do is to get a randomized factor 2 approximation algorithm. Okay. So the first step of this thing is we're going to distinguish between two cases. Either the size of the optimum solution is at least 60% of n, or it isn't. And now here's an interesting thing. What we care about is the weight of the optimum solution, right? We're trying to find some optimum solution of minimum weight. Yeah, but we're going to distinguish cases based on what's the cardinality. Yeah, so the cardinality and its weight are not the same things. We're going to be distinguishing the cases based on how big it is, like in terms of size. But in the objective function, what we care about is what's its weight. Okay, so case 1, opt contains 60% of the vertices. Then let me do the following crazy looking thing. Let V be the vertex that is in the 5th percentile. It's like the 5th percentile lightest vertex. Yeah. Then what you do is take V and all vertices that are lighter than it, add them to the solution, delete them from the graph, and decrease the weight of the other vertices, like the 95% that are higher than it. You decrease their weight by the weight of V. We will assume that all of the weights start out non-negative. So like it actually costs you something to pick a vertex. If it costs negative to pick a vertex, then you always pick it in the beginning, right? Then you're doing great. So we're assuming that all the weights are non-negative. And so notice that since all of the remaining vertices have weight more than V, when I decrease their weight by the weight of V, then their weight stays non-negative. Okay. Seems like a crazy thing to do. What I'm going to do now, I'm going to run the algorithm recursively on T minus what I already put in the solution with the new weight function. Yeah. And then whatever that algorithm returns, I will take that set and add these light vertices that I picked, and I will report that as my solution. And my claim is that if my assumption was correct, that opt actually contains 60% of the vertices, and the algorithm in the recursive call returns a 2 approximation for the recursive call, then what I output is a 2 approximation to the instance that I have. That's my claim. Okay, so let's prove the claim. Well, first, I claim that the weight of the optimum solution, G here should be T. I use G and T interchangeably. Yeah. So the weight of the optimum solution of G minus S with respect to the new weight function I compare it with the weight of the optimum solution to G with the old weight function. Yeah. Well, I decreased the weight of all the vertices that remained by the weight of G, by the weight of V. Yeah. And opt contained 60% of the vertices, and we removed 5% of the vertices. Yeah. So opt of G minus S contains so that optimal, like that solution now contains at least 55% of the vertices. And for each one of those, I decrease the weight by the weight of V. Yeah. If let's see. Yeah, so if the input is unweighted, then the first step is that if the cardinality of opt is at least n over 2, then you can just return all of the vertices of the G, and that is a 2 approximation. Yeah. 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 Okay. So if okay, so we're now comparing opt of G minus S with the new weight function with opt of G with the old weight function. Yeah. So pick the optimum solution to G that had 60% of the vertices. That is a feasible solution in G minus S. Yes, or yes? Now, that solution had 60% of the vertices. We got rid of at most 5% of vertices, so it has at least 55% n vertices left. And for each one of those, we decrease the weight by weight of V. So you get this inequality, yeah, because it's still a feasible solution of substantially smaller weights to the new graph. Now, suppose the algorithm, when I ran it on G minus S, was a 2 approximation. Yeah. Then, what am I saying here? I should say that this should be the algorithm for G, not for G minus S. There we go. Yes. What the algorithm outputs for G is a 2 approximate solution to G minus S. Yeah. But now, for every vertex in that 2 approximate solution, we increased its weight by weight of V. Yeah. And then we added the 5% lightest vertices. So, we add at most n times the weight of V to our approximate solution. Okay. But now let's do the math. This is, so I plug in this inequality for opt G minus S here. So I get 2 opt G minus n times 0.55 times weight of V plus n times weight of V. So I subtracted more than I added. So this is at most 2 times opt of G. How did I, okay. So the algorithm for G, yes, took a 2 approximation for G minus S with the new weight function. Yeah. And then it added the 5% lightest vertices, but also the weight function increased. Yes. But how much does it increase? Well, at most by the weight of V for all the vertices. And so there was 95% vertices left, weight of V, and the 5% that I added, 0.5. So this is at most n times weight of V. Yeah. And now, so it's at most 2 opt of G minus S times this, but now I have an inequality for opt of G minus S in terms of opt of G. Yeah, so opt of G minus S is opt G minus 55%. times weight of v. So I plug that in. I'm subtracting 1.1. I'm adding 1. So I'm left with 2 opt. Yeah, yes, exactly. Yeah. So I'm assuming that what I got back was a 2 approximation from the I got from the recursive call. Exactly. Yeah, so what we will get there. So I'm purposefully vague here. So yeah. Okay, so now comes the interesting step, which is the case that the number of vertices in opt is at most 60%. Yeah. Now notice we don't actually know which case we're in. The algorithm doesn't know. So it's going to do both. Yeah. But and we will have to pay for that in our running time. But turns out that that is not too bad. Yeah. So suppose now that opt is at most 0.6n, then what we're going to do is that we will pick a vertex uniformly at random, and I say that we succeeded in picking v if the vertex wasn't in opt, and both its out neighborhood and its out neighborhood and its in neighborhood contain at most 90% of the graph. That's what a successful picking of v is. Okay. Now, that's why we needed opt being at most 0.6n, because if opt is almost all of n, it's hard for a random vertex to not be in opt. Yeah. But as long as opt isn't everything, you succeed with 40% probability to be outside of opt. But now everything outside of opt, this is at least 40% of n, is acyclic. Yeah. Like this part, it's a feedback vertex set in a tournament. This is acyclic. Yeah. Take the first 0.1 n vertices in the topological order, the last 0.1 n vertices in the topological order. If you take any vertex except for those, yeah, then he is going to have these ones in his out neighborhood. Those ones is his in neighborhood. So both the out and the in neighborhood will be at most 90% of the vertices of the graph. Yeah. So in particular, I succeed with probability at least 1/5. Yeah, because you are here with probability 0.4, and then I took 0.1 here. I took away 0.1 here, so I have 0.2 left. I nearly look. So my definition of success in picking v was that v wasn't in the optimum solution, and that his in degree and out degree are not 90% of the vertex set. Yeah. Remember that in a tournament, the in degree plus the out degree is equal to n. Yeah. So I want to say that the vertex isn't extremely unbalanced. It's not like everything is in the out neighbors and nothing in the in neighbors, or the other way. So I want the neighborhood to be like somewhat balanced. Yeah. Well, we could pick from the set of vertices that are like that. The analysis ends up being epsilon easier if we just pick a random vertex. I mean, we anyway need to prove that there are vertices. I mean, we anyway need to prove that there exist vertices or many vertices that are not in opt that are here. Like in either case, we would have to prove those. And so here I'm doing this proof. Well, take the topological order, the first ones and the last ones. There's only a few, like if I take the first 0.1 and the last 0.1 and then everyone in the middle satisfy the thing I want. Okay. Now suppose we succeeded, right? That's something that happens with probability 1/5. So suppose v isn't in opt, then I claim that for every edge from its out neighborhood to its in neighborhood, one of the two endpoints must be in the optimum solution. Because if this one and this one and this one are not in the optimum solution, then here is a triangle that isn't in the solution, but that contradicts that it was a feedback vertex set. Yeah. So if we have a vertex that we know isn't in opt, V, then what we can do is, as long as there is an edge from the out neighborhood to the in neighborhood, we know that one of them has to be in the optimum solution. So now we can basically do a vertex cover style algorithm. Like in the unweighted case, you would just pick both and remove them. In the weighted case, the corresponding thing to do is you look at their weights, you decrease the weight of both of them by the smallest of the two, then one of their weights becomes 0, and then you pick the guy that just became free. Yeah, that's the, so as long as there is an edge where you know that the optimum solution contains at least one of the two, you do the following thing. You look at their weights, decrease both of their weights, not the weight of error, just those two vertices, decrease their weights by the minimum of the two weights. Then one of the vertices, at least one, becomes free, you pick him. Yeah, and I claim that if I now have a 2 approximate solution that avoids V, yes, after reduction, then I have one before the reduction as well. So let delta be the amount that I decreased the weights, right? Like the minimum of the two weights. Picking the 0 weight vertex is now free. So I'm only going to track what happens when I decrease the weights. Yeah. So the optimum of the tournament with respect to the new weight function is at most the optimum of the tournament with the old weight function minus delta, because I know that opt contained at least one of those two vertices whose weight I decreased. Yeah. So if I find a 2 approximate solution after the weight reduction, then that is going to be at most 2 times opt. So if I find a 2 approximation algorithm, 2 approximate solution after the weight reduction, then that is going to be at most 2 times the optimum after the weight reduction. And now I should remove the prime because I want to compare it with the old one. Yeah, but then what do? I just add 2 delta, because in the worst case, I contained both of the vertices whose weight I reduce. Yeah, but you know, now since in the optimum I decrease delta, I can pay for the 2 delta difference. So what happens here? 2 opt of TW prime is at most 2 opt TW minus delta plus 2 delta is at most 2 opt. Yeah. So in particular, this gives me this kind of algorithm. While there exists an edge in the wrong direction, decrease the weight of the 2 vertices, pick the one that becomes free, keep going. So what happens when this while loop ends? Then there are no edges from the out neighborhood to the in neighborhood, right? Because as long as there was an edge from out to in, I could delete the vertex. Yeah. But then these are different strongly connected components. Yeah. So I can solve the problem recursively or independently here. Then V is not part of any feedback vertex set anymore, right? You can just put him after the topological order of whatever you did here, and then solve this and put the topological order of this afterwards. Yeah. So now n minus and n plus are independent subproblems. So you can 2 approximate them independently as well. So now you just run your algorithm independently on the 2 sides. Yeah. And if you have a 2 approximate solution here and a 2 approximate solution there, then of course you get a 2 approximate solution overall. And the size of each of these 2 independent subproblems is at most 0.9n. So when I make the recursive calls, I make recursive calls on smaller subproblems. Why is that? Yeah. Yeah, we picked V so that n minus and n plus would contain at most 90% of the vertices, and that's where we use it. Okay. Now we're going to do the correctness. So there's two things we need to do. One is the running time analysis, and the other one is the correctness. The running time analysis is actually easy. Well, okay. I haven't described the algorithm yet because this is one step of picking V. So let me tell you what the algorithm is, and for that I want to tell you what property do I want the algorithm to have. So the property I want the algorithm to have is that it outputs a 2 approximate solution for this instance with probability at least 1/2, right? Like whenever it sees an instance, it will always output a feedback vertex set. And the probability that that feedback vertex set is 2 approximate should be at least 1/2. That's what I'm going to try to prove. Okay? I will assume that all of my recursive calls satisfy this specification. Okay? Now, what will the algorithm do? It will do first one thing. It will make a call to the case 1 situation. So you remove 5% of the vertices, and then you run the algorithm on the rest. Yeah, that was our case 1. It's just going to do that. Additionally, it's going to do case 2, but it's going to do case 2 20 times. So 20 times, it will pick a random vertex, and then if either the out or the in neighborhood is too large, it's just going to skip to the next of the 20 iterations. If it's not too large, then it does the n plus n minus while loop thing. Right? Edge in the wrong direction, pick one of the vertices, decrease their weights. And then when the while loop ends, you run the algorithm on n plus and n minus, combine the 2 solutions. And you do it 20 times, so you're going to get 20 solutions, keep the best solution. That's the algorithm. Okay, now there's 2 things: correctness and running time analysis. Running time analysis is actually ridiculously easy. We make 1 call to an instance of size 0.95 in case 1, and 40 calls of size at most 0.9 for case 2. So this is AT of 0.95 times 4, or it's like 41 times 0.95. Yeah. So by Master's theorem, this is some crazy polynomial time. It's not a very good polynomial time algorithm, but it's a polynomial time algorithm. Okay. If you optimize this, I think we managed to optimize this down to like 14 or 17 or something. Yeah. So now the only thing we're interested in is can we actually prove that with probability 1/2, the algorithm outputs a 2 approximate solution, assuming that all of the recursive calls do with probability 1/2, right? So now whenever I make a recursive call, what I can assume is that with probability 1/2, that recursive call returned a 2 approximate solution to that instance. Okay, great. That's why we do the 20. I mean, yes, which is why we do the 20. Yeah. So, okay, there are 2 cases. That's a good thing. In the sense that I think if I try to explain the question, I'm only going to confuse you more. So it's yeah. Okay, so what are we trying to do? We want to prove that assuming that every recursive call outputs, like whenever I make a recursive call, the solution it outputs is 2 approximate with probability 1/2. Now I want to prove that the probability that this recursive call outputs a 2 approximate solution is at least 1/2. Well, okay, there are 2 cases. Either the size of opt is greater than 60% or it's less. And I don't consider the probability of those two events happening, right? It is one or the other, and the algorithm would succeed with probability at least 1/2 in both cases. Okay, if the size of opt is at least 0.6n, I make one recursive call. That recursive call succeeds with probability 1/2. And if that recursive call succeeds, then this recursive call succeeds too. So great, this recursive, so if opt is at least 0.6n, this recursive call succeeds with probability at least 1/2. So now there is only the interesting case left, which is what if opt is relatively small? Well, let's look at a single iteration of the 20 for loop, right? I'll say that the iteration succeeds if the vertex wasn't in opt and n plus and n minus weren't too large. We already showed that the probability of that was at least 1/5. Yeah. Now, additionally, of course, I want the two recursive calls that I make to succeed. Yeah. The first one succeeds with probability 1/2. The other one succeeds with probability 1/2. So the probability that I picked v in okay way, 1/5 times 1/2 times 1/2, 1/20. Yeah. So the probability that a given iteration succeeds is 1/20. And if all of these things happen in an iteration, then the algorithm will find a two approximate solution in that iteration. Yeah, this is precisely what we analyzed before. If I got a two approximate solution from the right and from the left, then what I get is a two approximate solution for this instance. So now, what is the probability that none of the 20 iterations give me a factor 2 approximation? Well, it's 1 minus 1/20 to the 20, which is at most 1/e. The last visit from the inequality. Yes. And 1/e is, of course, at most 1/2. So we succeed with probability at least 1/2, and we're done with the induction. So we've now shown that this algorithm runs in polynomial time, and for every recursive call, it outputs a 2 approximation with probability at least 1/2. Okay, so that's all I had. Thank you.